In the last two lectures, we designed the current control according to the magnitude optimum and the speed control of an electric machine according to the symmetrical optimum. But there we assumed that we were measuring the current and the speed. Often the speed cannot be measured due to technological circumstances or for cost reasons, but the machine should still be speed controlled. Only the actual current value IA is available as an output. Thus, a state observer must be designed to estimate the speed n that is no longer measured. In control theory, a state observer or state estimator is a system that provides an estimate of the internal state of a given real system from measurements of the input and output of the real system. It is typically computer implemented and provides the basis of many practical applications. Let's simplify the whole thing in an example. The simulation model is now the DC machine extended by the power converter as a PT1 block, which also contains a state space block that represents the state observer and contains its state matrices. The block for the power converter is a PT1 element and formed as a feedback integrator. The electrical part and the mechanical part for the machine is already known. The state space block from the Simulink library will be used as state observer. For this, we will show now the basic setting for this observer. This file is used to initialize the general simulation data and to generate the state space LTI model SUS of the observed plants from URF to IA. Only the commands that are important in connection with the observer design will be discussed here. In order to linearize the Simulink model with the linmod command, all variables must be assigned a value. This also applies to the state space block, which is to contain the observer matrices, still unknown at this point. Therefore, these are pre-assigned with switchable values in such a way that no states are added to the system, and on the other hand, the number of inputs matches. The initial value vector obs x0 of the states is also defined. Since, for the calculation of the observer poles and the feedback matrix L, the state representation of the plant with the inputs U, the states X, and the outputs Y must be available. The state representation of the Simulink model is determined by means of the command linmod, and the corresponding state space LTI model of the plants is generated with the command ss state space. And we run the Simulink model. With this basic setting, this will be the change. The system input here is the set point speed UAref. The system states in this case are IA, the speed N, and the output of the converter block. The system output is the state IA for the armature current. Here, when creating the system with linmod command, the order of the states must be taken in account. These can be queried with the following commands. The states are the armature current, the speed, and the armature voltage. Now, after the observer initialization and the observer initial states initialization and creating state space LTI plant model for the system, now we can calculate the state observer. For this, which is simple by using MATLAB functions, but before we do this, we need some introduction to the observer design. The methods presented in the following are based on the representation of the systems in the state space and apply the theory of the state control and state observation, which is only presented cursorily and without derivations in the context of this course. For a more in-depth discussion of the theoretical prerequisite, please refer to the relevant literature. State controller is based on the principle of complete state feedback via the feedback matrix K, as shown in the right figure. The state controller thus represents a proportional controller in the feedback path. For the state controller design, the set point W is set to 0. The basic prerequisite for a state controller is the feedback of all states. That means all states must be measured, which is usually not possible in practice. Therefore, state observers are required to estimate the missing states from the available measured variables. The classical observer approach, according to Luenberger, uses a model that is identical to the plant. Via the feedback matrix L, the output error between the real output and the estimated output introduce the model behavior to the plant behavior. A common method for designing a state controller is pole placement, where the state controller feedback matrix K is calculated so that the poles of the closed loop correspond to the poles of a given desired polynomial. The Control System Toolbox offers two commands for this, occur and place. Both commands calculate the feedback vector K or the feedback matrix K in such a way that the plant poles match the poles spaced in the vector P, whereby the desired pole should not be multiple. The two commands differ in that occur is only switchable for CISO systems, whereas place is also switchable for MEMO systems. In addition, occur quickly becomes numerically unstable. In addition, place indicates how close the eigenvalues of the closed system are to the desired poles in PREC and stores a warning message in message for deviation greater than 10%. Just as for the calculation of the state controller feedback matrix K, occur and place can also be used for the calculation of the feedback matrix L of the state observer. Here, the system matrix A is transposed, and instead of the input matrix B, the transposed output matrix C is passed to the commands. In case of CISO systems, output vector C at occur. The feedback matrix L then results from the transpose of the results of occur or place. Once the feedback matrix L has been calculated, the observer can be created in a simple and quick way. The estim command generates the system equations of the state observer est. Back to our design. For the design of the Luenberger observer, the procedures and commands just presented are used. The design of the feedback matrix L is done with the command place. First, the observer poles polo are specified, which are then passed together with the transposed system matrices system.A transposed and system.C transposed to the command place, which again transposed calculate the feedback vector L. Finally, the stem command generates the LTI model OBS of the observer state representation, where the third parameter, sensors 1, is the measured output IA, the armature current, and the fourth parameter, known 1, is the known input URF, the reference voltage for the armature voltage. And when we run the simulation, we can remark that also the state space block has changed. And now we can plot the speed n and the estimated value of the speed. We can also plot the estimation error between the speed and the estimated value. After that, we can also plot the armature current and the estimated value of the armature current, and as before, also the observer error between the output armature current and its estimated value. The simulation leads to the curves shown in the illustrations. As can be seen from the estimation errors, the estimated values, the dashed ones, at the beginning of the block chipped excitation UARF correspond to the correct values. Also the error is 0. But after a low torque at 0.4 seconds, a considerable estimation or observer error remains. Why this remaining error we will explain and remedy in the next lecture.